Here we go. So, hi everybody. Hi. If you remember, right, we did this derivation for a simple harmonic oscillator that was going around in a circle. So we modeled it as something moving in a circle. And basically got this equation here. So again, on your equation sheet, it's this. So basically the big idea is this though. Like I kind of like this one better. So it says the position as a function of time for a simple harmonic oscillator is equal to the amplitude multiplied by cosine omega t, where omega is the, so yeah, A is the amplitude, T is the time, and then omega is what we call the angular frequency. And so, yes, and you can use sine or cosine. It just kind of depends on where your oscillator starts at, right? And mostly the goal is to try and find out what omega is. Once you know omega, you can pretty much get everything else. A is usually measured in some way, the amplitude, and then you can, right? And then once you got the position, you got this thing. You can take the derivative to get the velocity. You can take then the derivative to get the acceleration, et cetera, et cetera, et cetera. So the big thing is often trying to get omega. Now, so I'm going to start here, though, with showing you a different way that I can get omega. So it's not always going to be this way, but mostly it's going to be this other way I'm going to show you. So I'm going to get omega by basically using this simple harmonic oscillator here, but I'm going to use energy conservation. So I'll start here where the box is at so the box is a mass M. We're going to say it's got a spring constant K, like you do, right? So mass M, spring constant K, and then okay, and so here's my initial moment when it's at the positive amplitude, and then my final moment will be when it's at 0. So, and then I'm going to use energy conservation here. So we're going to say the initial energy is equal to the final energy, right? Because no friction right now. We're not going to worry about friction or anything like that. So energy is conserved. What type of energy would I have at the positive, at the amplitude? What kind of energy would I have at the amplitude? Spring potential energy. Yeah. Okay. We went over this before. What kind of energy would I have in the middle? Kinetic energy. Yeah. So it's going from spring potential energy to kinetic to spring to kinetic to spring to kinetic. So, all right. So we've got spring potential energy to start with, and then it turns into kinetic energy afterward. Okay. And so it's an ideal spring. So I can basically say that this is 1/2 times the spring constant times the displacement from equilibrium squared. And that's going to equal the kinetic energy, which is 1/2 mv squared. And well, let's see. So first off, the 1/2s cancel out, and then I get so, and then what's the displacement from equilibrium? What can I replace that with? Yeah, just the amplitude, right? So it's just going to be the amplitude. So it's going to be the amplitude squared. And then, yeah, so I got K times the amplitude squared equals the mass times the speed squared. And again, if I use that circle model, I can basically act like this is something that's moving with a constant angular frequency omega, right? For a circle of the radius that is the amplitude, right? So again, I'm acting like this thing is the same frequency, has the same angular frequency. The amount that this goes around is the same amount that this goes, one oscillation. So basically, I'm going to replace the speed at this moment as being essentially change that to like the angular speed where it is at this moment. Because when it's got its maximum speed here, that's when this is going the most, where all of the angular speed is basically the same as the linear speed here. So, and again, the radius we said would be from here to here, which is the same as that amplitude right there. So I can replace V with being omega times R, or sorry, not R, I'm going to say A instead of R. Or here, I'll start with R, but then R is the same as the amplitude. So I could take this, plug it in there. So it's going to be the spring constant times the amplitude squared equals M, and then this is going to be omega squared A squared. And what cancels out? A squared. Bye-bye. And so I can now isolate omega. And there you go. That's omega. And once I know omega, again, I got this thing. So typically we can measure we can measure the amplitude. So like that's always fairly easy to get, or usually it's gotten from a data point. But once you got omega, in terms of like things you know, which typically we can measure the mass and the spring constant of something, a couple things I could do, depending on what you're looking for. So if you want an equation of motion, this is the general solution. The position as a function of time is equal to the amplitude times cosine of omega t. So let's say I just know the amplitude right now. So cosine omega, I can replace omega with the square root of k over m. So the position as a function of time is the amplitude times cosine of the square root of k over m times the time. Boom. There you go. There's the equation of motion there. And then again, if I want the velocity, I just take the derivative. If I want the acceleration, take the derivative, etc., etc. Or another path I could take is, let's say I just wanted to know the period, right? So this is the angular frequency, but that's kind of weird because it's, radians per second, and that's kind of like, So often you want to get the period. Well, the period, this is on your equation sheet, is equal to, it says it's equal to 1 over the frequency, but it's also equal to 2 pi over omega. And again, that's angular frequency. So I can plug in omega here. And I got a fraction within a fraction. So I'm just going to multiply by the reciprocal. So this leads to that the period for a spring mass system, so this is for a spring mass, this is for an ideal spring mass system, is 2 pi times the square root of m over k. So there you go. When you look this equation up, people wonder where's the 2 pi coming from, right? And that's because we're converting from radians to like oscillations type of thing. So yep. And now officially of what we've gone over, you have 2 equations left on your equation sheet. Oh my goodness. Questions here so far before we go to the other method of doing it, which is typically what you're going to use. Because this next method we do is more powerful. this doesn't work all the time, but this next one is impressive. All right. So, differential equations. We are going to start and act. We're gonna once again, coefficient of friction is 0. And we got a spring mass system. Here I go. I'm displacing it, and my picture's kind of crappy, but you can imagine it's oscillating back and forth and back and forth here. So mass M, we'll say again, spring constant K. And so, yes. Oh, okay, yeah. That's a note to myself. Thanks, past me. Yes. So, there we go. So, go ahead, draw a free body diagram. So, at this moment here, I'm going to say it's not the amplitude. We'll say the amplitude, I don't know, is way over here. Again, my diagram's terrible, but. But yeah, we'll say the amplitude. So here's just some random point. Which way do you want it to go, left or right? Left. All right, sounds good. So the velocity is pointing this way. And so what I'd like you to do, again, here's the equilibrium position. It's over here. Draw for me a free body diagram. What forces are acting on the box? Sorry, box. The box is the system here. Just the box. Um, so, yes, what kind of cracks me up is you're so quiet all of a sudden. Is this the way to get you? Is it just because I have half the class here, or is maybe it's because though I'm filming, so all of a sudden like oh now I'm gonna be quiet. Yeah, I don't want to be immortalized on film. Yeah, Travis. It's just oh wow. All right, immortalized on film. There you go. The loud people are not here, or maybe it's because I have earphones on. Maybe that's part of it. Maybe I'm muffling you. That's probably why. Yeah. So Okay, what forces are acting here? Gravity, oldie but goodie. All right, so we got gravity. What else? Normal force. Okay, let's get to the more fun stuff. Spring force. Which way would the spring force point? Left. Yes, because we're displaced to the right, so the spring force should point left. Uh, okay. So there you go, and that's it. That's it, right? Again, no, we're ignoring air resistance. We're ignoring friction and everything like that. So then let's do F net equals ma. Yes, such fun. So okay. Now, I could do, X or Y direction, but I'm going to keep this. I'm going to keep this in vector form. So this is going to be kind of weird. I'm not going to put it in like the scalar form that we usually put in, where like you assign it a plus or a minus, and then you write it out. And I'll show you why just in a bit. So, okay, F net. So, well, even if I don't split this into X and Y parts, what's the net force equal to? Which force? The spring force. Yeah, right? Because these two would just cancel out. So we don't really need to even care about them. It's just the spring force that's acting here. So I can say, well, the spring force is equal to the mass times the acceleration. And again, there's the vector form here. So whatever direction the spring force is pointing, that's the direction of the acceleration, as we talked about already. All right. So now we have an equation for the spring force. That's Hooke's law. And it's equal to negative K delta X. All right. And so this is why I'm keeping the vector form, because I'm going to have this show up here, but I'll talk more about that in a bit and I'll plug that into the spring force. And I get this, negative K delta X, or I could say, let's say, we're going to make our, we're going to make our origin at the 0 mark. So if that's true, delta X is just equal to whatever this position is going to be, X. So I'll just call this X. So that means this is just going to be, 0 at the equilibrium position. Of spring. So if I do that, then this just becomes X. Negative Kx equals, and then the mass times the acceleration, and all that's in the vector form. So again, X points to the right, and so that means the force then points to the left. So therefore, then the acceleration points to the left. All right, let's start here. So now here comes then the differential equation part. Because I'm trying to find basically, usually in this class, we're trying to find the acceleration, yes? Like that's a big thing we often try to find, because again, if you get the acceleration, you can get the velocity, and you integrate to get the velocity, and you get the position, et cetera, et cetera. Let's say I'm trying to get the acceleration here, and so I'm going to isolate the acceleration. Well, actually, even before I do, now let's isolate the acceleration. So I'm going to isolate the acceleration, divide both sides by m. This is going to be negative k over m. X equals the acceleration. And here's, where you want to be on the lookout. I mean, if something's undergoing simple harmonic motion, it's going to be able, it's going to be described by this differential equation. We'll talk about differential equations in just a sec. But acceleration. What's another way to write acceleration? dv dt. Yeah, that is one way to write it. What's another way to write it? d squared x over dt squared. Right? It's the second derivative of position. So what I'm going to do is replace the acceleration term with d squared x over dt squared. Then I'll talk briefly about what this is that it means. So here is an equation where the thing that we're trying to solve for depends on its own, this equation, the acceleration here depends on its own, or the position, which is here, depends on its own second derivative, right? So because as the position changes, the acceleration is going to change. And so this is what we call a differential equation, where you have a variable that is equal to either its own derivative or its own second derivative or its own third derivative or its own fourth derivative or it could be equal to its own fourth derivative minus the third derivative plus the second derivative. Yeah, it's kind of weird. Yeah. So, and this is what we call a second order differential equation. So this particular one. So it's a differential equation. This is called a second order differential equation, or diffie-q. And so here's the deal. First step in differential equations is recognizing the differential equation. So first thing you want to do is recognize. Did I spell that right? Okay. Recognize. When you see this, you would go, oh, that's a second order differential equation. Because the acceleration depends on position, and acceleration is the second derivative of position with respect to time. Hey, that's you going like, ooh, yay, I know how to solve this now. Then isolate A. Completely. Third step. Replace A with d squared x over dt squared. This is you telling the reader, I know this is a second order differential equation. And you're almost guaranteed, probably on an FRQ, where they're going to say, here's a spring mass system oscillating, blah, 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 blah. Derive this, write out the second order differential equation of this thing. And so you would do exactly what we just did. Free body diagram, F net equals ma. The acceleration depends on the position. And then you can isolate the acceleration and replace the acceleration with d squared x over dt squared. And then usually that's like worth 1 point right there, just by replacing that. Or usually, often it's applying Newton's second law, there's 1 point there. Replacing the acceleration term with d squared x over dt squared, that's 1 point there because that's you saying, I know this is a second order differential equation. Yeah. A couple things about this is it has to depend, the acceleration needs to depend linearly on the position. It cannot be x squared. It cannot be x cubed. It cannot be the square root of x. If it is, doesn't obey Hooke's law, not going to be simple harmonic motion. It's got to depend linearly with position. Yeah. K and M, they could be anything. You could do K squared. This could be a B. This could be a whatever. Yes. And so the next step, once you do this, and this is the thing, there's like next to no algebra here, because the next step is this: is you go, this is a second order differential equation. I know the solution. I know the general form of a second order differential equation. It's this. It's called the general form. So for a second order differential equation, if you make it look like this, whatever is in front of the x, not the negative, but whatever's in front of the x is equal to omega squared. Now, for whatever reason, they don't have this on your equation sheet. This is something to memorize. But again, once you do so, questions here so far? So, what's omega squared equal to? Using my equation here. K over m. Omega squared then must be k over m because that's what's in front of the x. And this is completely isolated. So omega must equal the square root of k over m. Which, if you remember, was exactly what we found out using energy. Oh, supporting evidence. Same thing. And then I can plug this into the general solution, which is on your equation sheet. The general solution for a second order differential equation is this. Again, it could be sine, it doesn't have to be cosine. Oh, God. And so I could plug in omega, yada, 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 yada. So here's the deal, because I want to, before things end, I want to show you, because for some reason students go like, it's the x squared and the d squared, and all these wacky things are happening, and with omegas now, and I can't do this. I've never done this before. Yes, you have. Yes, you have. Yes, you have. Yes, you have. What's this? That's a quadratic. Ooh, you recognized it. You saw it and you said like, oh, that's a quadratic. Do you know how to solve quadratic equations? Yes. What do you do? Oh, God, you've memorized it. It's amazing. Oh, negative, yeah, negative b plus or minus the square root of. Oh my God, that's amazing. That's amazing, right? Well, but how do you know what b is? What's b? Negative two. How'd you do that? It just is. Oh no! Thank you. The general formula for this is ax squared plus bx plus c. So what is this then? General solution. This is the general solution of a quadratic. And basically what this says is you put the quadrat, right? Once you recognize something as a quadratic, you go, oh, I have to set it all equal to zero. Why? That's the general formula. The general formula is this: ax squared plus bx equals plus c equals zero. And once I do that, I can use this general solution that I've apparently all of you have memorized, right? And I just plug it into that thing, do a little bit of algebra, and out pops my answer. Honestly, the algebra here is harder than the algebra in what I just showed you. So, what the second order differential equation is you're doing F net equals ma like you always did, but then once you go, oh, that's the acceleration. It depends linearly with position. That's a second order differential equation. I know the form of a second order differential equation. It's negative omega squared x equals d squared x over dt squared. And right, because you know that, you, just like you set the other one equal to zero, you isolate the acceleration term and replace it as d squared x over dt squared. Again, this is you telling the grader, I recognize this. I know this is a second order differential equation. And you do have to replace that. That's usually where you get your point. And then you go, well, and the general solution is I just pluck out whatever is in front of the x. Why? That's the form. And so you just pluck it out because whatever's in front of there, that's omega squared. Isolate omega, plug it into the general solution, which is on the equation sheet. Questions here so far? Now, as to why is this the general form and things like that, I showed you somewhat using physics terminology and things like that. You'll find out in math class. But I do have to say, so we're going to do one other type of, well, we're going to get practice with this. We're going to do other types of things. And this is very powerful. Like we're going to be able to do for people that took physics before, we can only do ideal pendulums and ideal this and ideal that. We're going to be able to do a lot of different things because of this thing. But the other type of differential equation we're going to do is first order differential equations. That'll come, that's like one of the last things we do. But, and again, we'll have methods to solve for this, but I just have to, as a fun little fact, differential equations are like, kind of like integrals where they're like a challenge to solve. They're like, kind of like, and anybody encountering them is like, ooh, how do I approach this, type of thing. And literally a method for trying to solve a differential equation is guess and check. Let's assume the answer is this. Nope. So yeah. Okay. So yes, once again, the process is, it's almost, yeah. So process, free body diagram, F net equals ma, plug in your force, and then obviously if it's Hooke's law, you replace it with that. If the acceleration depends linearly with the position, replace it with d squared x or dt squared. We'll get practice on this on Monday. All right. See you guys. Bye, everybody at home.